In the last video, we talked about finding arc length, and that was finding arc length between two fixed points on a curve. So we were looking for a number, okay, and that was measuring the length of the curve between those 2 points. In this video, I want to talk about s of t, which is going to be the arc length function. And I really ought to call it the signed arc length function. We'll have to talk about what that means in a moment. Okay. But this is going to be a function where I plug in a value of t, and the number that it spits out represents an arc length. Okay. So here's how that works. We're going to have r of t. It's going to have to be continuously differentiable. That was a condition needed for that arc length formula to be valid. And I'm going to suppose that this has an orientation. The book makes a slightly different requirement. They just say that we just trace the curve just once. I'm saying we want to have an orientation. What we're both trying to avoid is a situation like this, where we have a curve where we're going back and forth and retracing, but changing direction as we go. The book, by saying that we trace the curve exactly once, just if we had such a curve, would restrict the domain so that we're just talking about one tracing of that. By saying that I've got an oriented curve, also I would have to, for something like this, restrict the domain so that we're getting just one portion of this. But I'm allowing for a situation like with the unit circle, where it's oriented, we trace it again and again and again and again and again. So we do retrace the curve, but we do that without reversing direction. Okay. All right, so if we have that, we can define this thing called the arc length function. And here's how it works. So here's my oriented curve. I'm going to have some point that's my reference point. So that's going to be, that point will be the tip of r of t naught. Often we will choose t naught to be 0, but it doesn't have to be. We pick some t value and the corresponding location on the curve to be our reference point. And what we're going to do is we're going to measure arc length from there. Okay. So this curve is potentially infinitely long, but I can say, oh, if I'm here, what's my arc length? Well, what's my arc length between my reference point and here is what we're going to mean. So we find that by saying s of t would be the integral from t naught to t. So notice my variable is the upper limit of integration, magnitude of r prime of u du. I'm going to have a dummy variable here. Remember, I can't let t be both my upper limit of integration and the variable with respect to which I'm integrating, because here we're saying our variable u is taking on all values from t naught to t. T can't do that. It's busy being itself. Okay? So you do need to have a dummy variable here. Now we call it a dummy variable because it's going to drop out. We're going to take an antiderivative with respect to u. We're going to replace all the u's with t's and t naughts, so there won't be any u's in our final answer. But do be careful with that. That's a notational issue that a lot of students get caught just making a mistake and writing something that really doesn't mean anything. If you have a dt here and a t here, it just doesn't make sense because you're telling me two different things. T is here, and t is taking on all values in between. Can't do both. Okay, now I called this the signed arc length function. That's because, notice, our integrand is never ever going to be negative because it's the magnitude of this thing. So, with the exception of a few places where it might possibly be 0, as a general rule, this is going to be a positive thing, and it's going to give me a positive arc length. If this is the direction of increasing t, I'm getting a positive arc length here. But notice, if t was smaller than t naught, that would put me at some point here before I hit the point that I hit at t naught. If that's the case, I've still got my non-negative integrand, but now I'm integrating backwards because the smaller number is on top. And I know if I integrate from bigger number to smaller number, that's going to give me the opposite of what I'd get if I integrated from smaller to bigger number. So that's going to give me a negative arc length. So essentially what's going to happen is at this reference point, S at T naught will be 0, because then we'd be integrating from T naught to T naught, so we'd get 0. For T values bigger than T naught, we're going to count that as a positive arc length. And if you get a positive arc length, that just says you've moved past the reference point. For T values before T naught, we would be getting a negative signed arc length. Now I have to say it's a negative signed arc length because arc length can't be negative. Signed arc length can. And what the sign means is just that we are at a point before that. So if my arc length was signed arc length was -3, I would say, okay, I want to travel 3 units back from my reference point. Whereas if my signed arc length was +3, I would want to travel 3 units forward from my reference point. Okay, so this is going to be a function that tells me for each moment in time, if my parameter is time, or for each value of my parameter, what is my signed distance from this reference point. Let's look at an example of finding an arc length function. I'm going to let r of t be t cubed over 3, t squared over 2, with a restricted domain that t is bigger than or equal to 0. That's a necessary restriction that we'll see why as we work through this problem. Okay, and I'm going to let t naught equal 0. Okay, so I'm going to use the starting point, the literal starting point of my domain as my reference point. Now, what that means is that my arc length function will only be spitting out non-negative arc lengths because we don't have any t values that are less than our reference point. That's fine. Okay, so the arc length function would then be s of t would be the integral from 0 is my reference time to t, magnitude of r prime of u du. Do not forget that you need to introduce that dummy variable. All right, so let's go ahead and calculate what that is. Now, I only need the dummy variable in the integration. So if I wanted to just calculate r prime of t and then the magnitude of r prime of t, writing it in terms of t's, that's fine. But I'm an absent-minded professor, and my guess is many of you are absent-minded students, and it's really easy to forget. So I'm going to just introduce the dummy variable now. So I'm going to just rename that my parameter u and get u cubed over 3, u squared over 2, u greater than or equal to 0. This is exactly the same curve as this because all we've done is we've renamed what the parameter is. Okay, so then r prime of u is just u squared u. The magnitude of r prime of u is the square root of u squared squared plus u squared. So that's the square root of u to the 4th plus u squared. I'm going to see if I can't simplify that. Okay. Anytime I'm finding an arc length or an arc length function, I'm going to be integrating a square root. In general, it's going to be very helpful if I can pull some stuff outside so that I can do a substitution, or in some cases, I might even have a perfect square under the square root. We saw that in our last example, and be able to simplify the whole thing. As a general rule, when I get to this point where I've got the square root of a bunch of stuff, it's not going to be in a form that's easy to integrate. It does look like here I could factor out a u squared. Okay. And now square roots do distribute over multiplication. They definitely do not distribute over addition, but they distribute over multiplication. So this is the square root of u squared times the square root of u squared plus 1. The square root of u squared would be the absolute value of u times root u squared plus 1. And now we see why I made that original restriction. we said that our parameter, and we've switched from calling it t to calling it u, had to be non-negative. That allows me to simplify this. I can say u is bigger than or equal to 0 to u root u squared plus 1. If I hadn't put that restriction on my domain, I would have to leave this as the absolute value of u. Now I could do that, but then I'd have to integrate this piecewise, because I'd have to say that's u if u is bigger than or equal to 0, but it's the opposite of u otherwise. Okay, excellent. So, s of t is the integral from 0 to t of u root u squared plus 1 du. Now, that looks like it's not too bad to integrate. I'm thinking a quick w substitution will do the trick. So let's let w be u squared plus 1. dw would be 2u du. So I could use a 2. I will introduce a 2, counterbalanced with a 1/2 on the outside. And so we'll have 1/2. The integral from the w value at 0 would be 0 squared plus 1 is 1. To the w value at t is t squared plus 1. And then we're looking at w to the 1/2 dw. All right, so that's going to be 1/2. Antiderivative of w to the 1/2 is just 2/3 w to the 3/2. And we're evaluating that between t squared plus 1 and 1. Those 2's will cancel, so I'm going to get 1/3 of, let's see, t squared plus 1 to the 3/2 minus, I'm going to just put this in brackets, factor out that 1/3 so that it applies to both terms. 1 to the 3/2 is just 1. If you wanted to distribute that 1/3, you certainly could. If you want to keep it factored out, that's totally fine. That is my arc length function. Okay. All right, excellent. I will just point out, if t is 0, this becomes 1 to the 3/2, which is 1 minus 1, which is 0. We get 1/3 of 0. That should always be the case. The arc length at your reference point should be 0, because if you're at your reference point, you are 0 units away from your reference point. Okay. And then for anything that's bigger than 0, this is going to be bigger than 1, so I am getting something that's positive. So I'm able to see that. Okay. Excellent. So there's our arc length function for this particular curve.